right, everyone. I'm going to go through the study guide for exam number 2 and talk about some of the different sections. I'm going to start just because I prepped it, or at least I have stuff in front of me for the chapter 5 stuff. I'll come back and do chapter 3.5 either at the end or in a different video. I might just split these up into different videos. Okay, so let's look at what we're talking about for chapter 5. I'm just reading off the list that we have here. We want to know the definitions of cations and anions. That one you should know. Cations are positive, anions are negative. What does it mean? How do I form a cation? And that gets into the protons and the electrons in the atom. So the balance, the imbalance gives you a charge either positive or negative, depending on which of the subatomic particles you have more of. Either protons, more protons, it's going to give you a positive charge. More electrons is going to give you a negative charge. Okay, so be able to predict the charges of ions from their location on the periodic table. All right, so you see on the screen that we've got our periodic table. This one that I chose, unfortunately, does not have the proper group numbers. So let's go to another one. Okay, so we loaded up this other table. All right, so normally we have the group numbers, 1A, 2A, through 8A across the top, and those are for our main group elements. And so those don't take into account the transition elements here in the middle. They're just the main group elements. Okay, so predicting charges, remember that for the main group elements, number 1, 2, and over here, number 3 for the metals, that we can define what their charge is going to be by the group number. So group number 1A are going to be +1 charge, so these guys are +1. Group number 2A are going to be +2 charges, or 2A. And over here, for starting with aluminum, because it's the first metal, we're going to be +3. And these other ones, we don't really talk about those very much, but those are indeed also +3. They have some different things that they do because they're on the other side of the transition metals. So we won't worry about that. Okay, and then on the other side of the periodic table, the last row, those are our noble gases. So those noble gases, they don't form ions, so we kind of ignore those. And we're going to step down the opposite way. We went on this side, we went 1, 2, +1, +2, +3. And on this side, we're going to go -1. So fluorine, chlorine, bromine, those all form -1 charge ions. Oxygen, sulfur, selenium, those are -2. Nitrogen, phosphorus, -3. All right, the next little bit is to be able to name cations and anions. So for cations, if we know what the charge is, then we don't need to give it any kind of indication. So for the ones that we know, which are group 1, 2, and aluminum in group 3, we know those charges. It's always +1, +2, +3. Let me see. All right, so let's see. I had to pause it. I changed it to an arrow. Hopefully you can see this a little better. I'm not sure. All right, so if we know the charges, so group 1, group 2, those are +1 and +2, then we don't need to put the Roman numerals. And well, the Roman numerals are going to be for the ones that have variable charge. These are usually the transition metals and 1 or 2 of these other non-transition metals. Okay, so if I have a lithium ion, I just name it lithium ion. If I have a magnesium ion, it's just named magnesium ion. Aluminum ion is going to be aluminum ion. So if I have one of these transition metals, let's take iron for example. Iron can have a variety of different charge states, and the charge states for iron that we know of are +3 and +2. There are others, but Those are the ones that we know, and it doesn't really matter. So if I want to name an iron, I have to give the charge on that ion. So if I have Fe2 plus, then I'm going to write that out as Fe2 plus. All right, so I would write, and I'm writing with my mouse, so sorry about the sloppiness, Fe, and then we're going to put Roman numeral 2, it's a terrible 2, but you get the idea, Fe2, and that indicates that I have an Fe iron 2 plus ion. Okay, so for when we're naming those ions of the transition metals, we need to include that Roman numeral in a parentheses, and we give that the name Fe2 ion. All right. So now when we want to name anions, remember anions are over on the right-hand side above the stair step, which is not shown on this periodic table. But normally you have that stair step coming down here. So these are all nonmetals, and nonmetals are going to be the ones that form anions. Okay, so in our anions, when we want to name those guys, we take the root of the name. So let's look at fluorine. Fluorine, you take the root fluor and add IDE. So this is going to form a fluoride ion. This will form a chloride ion, and this will form a bromide ion. Okay, so same step here. Anion, negatively charged, you should know that the oxygen is going to form 2- ion, and we're going to call it an oxide ion. And we're going to call a sulfur a sulfide ion. And then nitrogen is nitride, and phosphorus is phos, that's our root, phosphide. Okay, so that's how we're naming ions. Okay, so switch screens again so I can write on my pad and talk about the next thing. All right, so understand that ionic compounds are formed when cations and anions are held together by ionic bonds between oppositely charged ions. Okay, so remember that we talked about sodium and chloride. That was our one example, or we've had that example, and that it's made up of Na plus ions and Cl minus ions. Okay, and that it's not only 2 of those in our compound, but it's a huge array of those guys. So Cl minus, Na plus, I'm not going to write them all out. Cl minus. And this is a big 3-dimensional, there's many 6 times 10 to the 23rd on that order of those ions in our formula. And when we write our formula for our ionic compound, a couple of steps, and that is the charges have to balance. So Na plus is 1 plus, Cl minus is 1 minus, so the charges add up to 0. So the overall charge for this guy, for the whole compound, is going to be 0. And we don't write out like a molecule does, like if we said water is H2O, that means we have 2 hydrogens and 1 oxygen. For these compounds, we write the ratio of the ions. So in sodium chloride, I have 1 sodium ion for every chloride ion. And that's the way we write our formula. So if we were to write that formula for CaCl2, that is compound composed of Ca2 plus ions and Cl minus ions, but there are two of them. Squeeze that in there. Let's get rid of that. That wasn't good. All right. So again, we don't have a molecule of CaCl2 because these are ionic compounds. So we form many of those ions all put together. But if I was to look at a calcium chloride a solid of that, if I could see it, I would see that there are twice as many chloride ions as there are calcium ions. So I would write that CaCl2 because there's 2 times as many chloride ions in my solid, in my ionic solid. And we call that the empirical formula. So the empirical formula is the smallest ratio of those atoms that I have together. So the empirical formula for calcium chloride is CaCl2. An example of, so for example, if I would never write Na2Cl2 because that is not the smallest ratio. There's 2's there, I can divide everything by 2. So I wouldn't write that, and I would write NaCl. All right, so the next point is be able to predict the formula of an ionic compound given the name of the cation and the anion, and, or the name of the compound. So we know that an ionic compound is always charge neutral, right? So those charges are always going to add up to 0. Okay? And that's super important. That's what most people struggle with, is making sure that they add up to 0. So you must be able to balance the number of charges from the cations with the number of charges from the anions. All right, and the example that I give there, an example would be calcium oxide. So if I said I had a compound that was made of, I could write this out as calcium ions and oxygen. Or I could just say, what if I have a compound that's made of calcium and oxygen? So what you would need to know is you would have to go in and say, okay, calcium, if it's an ion, what is the ion? Okay, so look at the periodic table, and I see it's in group 2. So it's going to be calcium 2 plus, it's the metal. And oxygen, I look at it's in group 6, so it's oxygen 2 minus. Okay. So those are the ions that are going to form from calcium and oxygen when I have an ionic compound. All right, and I put those two things together to form the compound CaO. All right, whoops, that's not Cu, that's Ca. Calcium oxide, okay, because the 2 minus and the 2 plus charges balance out here of a neutral compound, okay? And I want to emphasize, when you write a ionic compound, we know that it's made out of ions because it's a metal and a non-metal. Okay, so we know that that means it's made out of ions, but we never write the charges on those ions. So I write it as CaO. I would not write it as Ca2 plus O2 minus. A lot of people make that mistake, so we don't want to do that. It is not Ca2 plus O2 minus. Those charges are implied, and we write it the correct way as CaO. Another example would be if I said I have a compound, or I have, let's say I have a compound formed between a calcium ion and a nitrate ion. Okay, so that would be a question. So you would need to know, okay, well, we just did calcium. Let's stick with calcium. So calcium ion, you need to know that it's a 2 plus ion. And you also need to know nitrate. Okay, so what is a nitrate ion? Okay, I remember the nitrate would be, oops, let's go back to our NO3, that's the nitrate, and because it's an ion, it's minus. So I'm going to form a compound between Ca2 plus calcium ion and a nitrate ion. Okay, so that's a polyatomic that always stays together as a unit. So I always, when I have NO3 minus, it sticks together, it doesn't break apart. So I need a certain number of those to match the number of charges that I have on the 2 plus from the calcium. Okay, so when I write a chemical formula for that, I'm going to write calcium, and I know that it's 2 plus, so I need to balance it with 2 of these NO3 minuses. Okay, so the charges minus 2 is going to add up to the plus 2 from the calcium. So I need to draw a parentheses, NO3, and I need 2 of them. So I have 2 units of NO3 minus in my formula. And again, I'm not writing the charges in my formula. Okay, so that's an example with a polyatomic where I have an ionic compound. And again, whenever we're doing the ionic compounds, metal, non-metal. Okay, metal and non-metal. All right, so the next thing on our list is be able to name ionic compounds given their chemical formula. Okay, so let's take a look. I'm going to just write one out. Na, let's do this one, NaNO3. Okay, so you should be able to name that ionic compound by looking at those components. So I look at what's my metal, and the name of that is going to be sodium. Okay, so that's my Na part. And my nonmetal, and that is nitrate. So that's one of my polyatomics, a common one. Okay, so when I put those two things together, I name the cation first, sodium, and then I name the anion, nitrate. Now, if I had, let's say here, this one's different, Na3N. Okay, so what are we going to name that? Now, for these compounds, we don't need to give the charge on the sodium because it's always +1. And also for this compound, we know the charge on the nitrate, it's always -3. That's why we have 3 sodiums for each nitrate in this. So when we're going to name this compound, we're going to name it just sodium. And because we already know the charge, we don't need to put anything else. We should just name it sodium. And in this case, it's not nitrate, it's the root nitride. Remember, we had the IDE for the nitrogen, nitride. So there's a big difference between these two compounds, sodium nitrate and sodium nitride, even though their spellings are pretty close. Okay, so that's how we would name that. Now, that's when we know the charges. Okay, and we're always going to know the charges on the anion, but sometimes we won't know the charge on the cation. Okay, so some of the variable, the cation can be a variable charge. Okay, so let's do an example of that. So if I have, let's pick, I have a compound and the name is, oh wait, what are we doing? We're doing formulas, sorry. Okay, so I have Fe, I'm going to do that, Fen. Okay, and I want you to name that compound. Okay, so first thing I look, what's my metal, what's my non-metal? This one, iron's going to be my metal, nitrogen's my non-metal. Now I know the nitrogen and the anions, I'm going to know their charge, right? So I know that the iron or the nitrogen is 3 minus, okay, because it's in group 5. So that means if I have a neutral compound, iron nitride, oops, I gave away the answer, then this one has to balance the charges, right? So the iron must be +3 in order to balance the charge. I have the equation of the compound that I form, Fen, So that means that I have one iron, so it's going to be 3 plus, because the one nitrogen nitride I have is 3 minus. So when I write the name, I have iron, and I have to say what the charge is. Iron 3 nitride. Okay, iron 3 nitride. Let's try the nitrate, do similar to what we did before. So what if we had this compound, FeNO3, 2. Okay, again, we know the charge on the nitrate. We know that anion charge, it's always -1. We have 2 of those -1 charges, it says right here, we have 2 of those charges. So that means -2 is being brought by the anion. So if that's -2, that means our iron has to be +2. +2. Okay, so when we're going to name it, we're going to call it iron. We give the charge in the parentheses, 2, and then we say nitrate. All right, so for our next point, understand how neutral solids with 0 overall charge can dissolve to form charged ions in solution. Okay, so that goes back to where we were showing the solubility of things and things dissolving into water. So the way that we show that in a formula is, let's take our KNO3, that's potassium nitrate. So we take that and we put it into water. Whoops. We put that into H2O. So we say we dissolve potassium nitrate solid in water. So remember, it's going to split up into ions. If it's soluble, then it's going to break apart into the ions that are forming it. So we wrote our equation. We didn't put the charges, but they're implied. We know that that's an ionic compound and it's stuck together. Those ions are stuck together, but the water can pull them apart. And when it does, you put it into water, and what comes out is going to be K plus ions. We put our aqueous plus NO3 minus ions. And that's aqueous, right? So our neutral compound that's made up of the ions, equal numbers, splits up, and those ions float around in our solution. And that's what we see, that's what is shown here. The aqueous, meaning they're in solution and they're floating around. So water is surrounding those ions and allowing them to move through the solution. And we remember from our lab that that's what allowed electricity to flow, because those ions are able to move around in the water. So if I had potassium nitrate solid, no electricity would flow through that because they're not mobile. But for potassium nitrate in solution, ions can move so it can conduct electricity. So that brings us to our next point. Know the terminology for aqueous solutions and electrolytes, including soluble, when things will dissolve, insoluble, they do not dissolve, and then whether they are strong, weak, or non-electrolytes. Okay. Okay, so remember from our lab that we talked about the fact that when I take ionic compounds and I dissolve them, there are some types of compounds that ionic solids that are soluble, will dissolve in water, and will do exactly what I just that is shown on the screen here. Okay, so they split up into ions, and we say that we show that when we put them in water, they split up completely into ions. So we have that arrow that points that way, meaning it goes completely one way. So none of it is left as the KNO3 solid, and it's all formed as ions in the solution. Okay, so that is what we call a strong electrolyte. Okay. We had another one where we talked about strong acids. And an acid is defined, you don't need to know the definition of an acid right now, but acid is defined as something that gives H plus ions in solution. So when I have HCl, it's a strong acid, meaning it's a strong electrolyte. Put it in solution, and I get H plus ions and Cl minus ions. And we write the arrow this way because that means that none of it stays as HCl as a molecule. All of it splits apart into ions floating around in their solution. And then HCl, strong acid, will conduct electricity readily. Okay, so then we also saw that there are things called weak acids. There's weak other things, but the most common thing that we talked about was a weak acid, and that's vinegar or acetic acid. And if we have pure vinegar, all non-metal, right? So pure vinegar, this is one of the special things because it's what's called an acid. It's all non-metal atoms. We don't consider it ionic. But if we take acetic acid, pure, it doesn't break up into ions. It stays together, attached together as a molecule. This is one of the questions in the lab. Okay, but if we put it in water, water has the ability to go in and break that molecule apart in one specific location. Most of it stays together, but the water can break a very certain bond, and that's that hydrogen that's on the end. So what happens when we put acetic acid into water is we draw our little arrow going one way and the big arrow going backwards. Okay, so that's telling us that not much of this guy is ionizing. So it's a weak electrolyte. And what I'm forming over here is the portions that split up. So CH3COO minus, and it breaks that hydrogen off and it comes off as an H plus. Okay, and the equation shows us that we make few ions. So this is weak. So this doesn't happen very much. We don't have a lot of those ions in solution, but we have, and we have mostly molecules. And our arrow in our equation, our arrows show that. Okay, and then finally, we have things that are non-electrolytes. Okay, and we talked about those. Acids are special cases of nonmetals. So if I have sugar, solid, that's all nonmetals. But if I put sugar in water, it doesn't split apart into ions. All I get is, whoops, C6H12O6 aqueous. Okay, it stays all together, non-electrolyte. Ran out of space. Many non-metal compounds are like that, where they're covalent compounds, and because they're covalent compounds, they stay together. They don't split apart. Okay, so when I put that in water, if I dissolve it in water, I get no electricity because they're non-electrolytes. Okay, and then finally, the other type of non-electrolyte is if I have a solid that doesn't dissolve. So if I put something into water and it doesn't dissolve, the dissolving part is the water breaking up the bonds. So if it doesn't dissolve and water can't break up those bonds, then I'm not going to get any ions either. So I always use the example of calcium carbonate, seashells. That's a solid. If I put it in water, it's not going to do anything. It's not going to dissolve because it's insoluble. Okay, so if it's insoluble, water's not strong enough to come in and break apart the calcium and the carbonate from each other. So it won't dissolve and it won't form ions in solution. So So if I drop a seashell in water, it's not going to conduct electricity. All right, so I think that wraps up at least the sheet for ionic compounds. So we'll move on to the next one in the next video, I believe.